This lesson is on projectile motion. If you haven't seen the free fall lesson or haven't gotten the free fall lesson, you should go watch that one first. So a projectile is an object that's in free fall, which is near the surface of the Earth, but it has a horizontal component to its motion. And in free fall, we've looked at objects that, we have a baseball here, objects that go up into the air, or the baseball is falling, or even a combination of both. It goes up and comes back down. I mean, really, would just be in one dimension. So goes up and comes straight back down like that. Projectile has not only does it go up and it starts coming back down, but it also has a horizontal motion to it, so it's moving in this dimension as well. Something to note about projectile motion is, of course, we remember that the vertical motion, there is acceleration due to gravity. It's a constant vertical acceleration, and we said that's 10 meters per second downward. Horizontally, though, of course, gravity doesn't work horizontally. There is no acceleration horizontally, and so your horizontal velocity will be constant. And we'll see that here in just a moment. So for projectiles, we have to kind of modify our variables, um, and as well as the equations that we use. So for position, horizontally, we've used x naught and x for the initial, or for the initial position and the position later in time, or position at time zero, position later in time. But if we're talking about vertically, then we have the initial height, y naught, and we have the height later in time, which is y. For velocity, we have a constant horizontal velocity, but vertically we do have your velocity, your vertical velocity at time zero, and your vertical velocity at some later time. Vertically, there is acceleration. Horizontally, there is no acceleration. And of course, both of them will use t for time. These are our modified equations. You'll recognize the ones on the right. And the one on the left here, you'll recognize is when you realize that this is just one of the three equations that we have. But because there is no horizontal acceleration, in other words, a is 0, as we wrote there, well, this term goes away, this term is 0, and this term over here is 0. And so what we get is this, this, and this. And that's why we left out these other two, is because these statements aren't very useful. They're not useful at all, actually. And so this is the only horizontal equation we have, and these over here are our vertical equations. Cool, I think we'll do an example. It says Otis the cat runs at 3 meters per second, running on a table. So Otis runs over the edge of a 1.4 tall table. So Otis will go run this way. And what's interesting to note here is that Otis is not jumping up. When Otis reaches the edge, Otis does not jump down. Otis is just running straight. Otis is running horizontally and will begin to fall once the table's edge is met. So Otis will start to fall here. We want to know how much time does it take, so for Otis to land here, and how far from the base of the table, in other words, this distance, if this is x naught and this is x, in other words, what is x? How far does Otis land from the base of the table? We're going to make two lists of variables. We have our horizontal and our vertical. And we can start putting in some numbers in these lists. Let's start horizontally. We're going to put 0 here for x naught. We don't know x. We do know the horizontal velocity, which is given here in the image, 3 meters per second. And time we don't know. The initial height of Otis is 1.4 meters. And the final height of Otis, I shouldn't say final height, but the height at time t, be 0, would be the ground. So the ground is 0 height. Now the initial, or the vertical velocity at time 0, so although Otis has a horizontal velocity, Otis does not have a vertical velocity yet at that moment, at that instant that Otis is not jumping off it, but is running off the table. You can think of it as Otis is dropping, right? So remember when we said that when something is dropping, that initial vertical velocity is 0. Okay, we don't know Vy. We know acceleration. This is from the free fall lesson. Is the acceleration due to gravity is -10. Cool. So selecting an equation, we want to figure out how much time does it take for the cat to land on the floor. Well, we've only got one equation which uses all of these variables. Horizontally, we only have one equation. And we would need 3 of these numbers to solve for anything, so we're not going to use the horizontal equation. We have 4 numbers in the vertical list, and so that's going to be good for us to figure out time. Which, if we come over here and looking for an equation in our vertical equations for time, will not be this one because we're missing Vy. So it's the only other equation with time, which is the second one. So we will put in some numbers here, 1.4. Vy naught is 0, so 0 times t is 0, so this whole thing is 0. And so I'm just going to keep writing 1/2. Acceleration is -10 t squared. We will often get 1/2 times -10 would be -5. So you just remember it. Cool, we need to solve for t. I like to add 5t squared to both sides of the equation. We'll divide by 5. So 1.4 over 5 is 0.28. And then we need to take the square root. 0.53 seconds. So we can put it over here. Just remember that we do grade it with the work over here. We don't grade it from the list. The answer, that is. Cool. Now we have 3 numbers in our horizontal list, and of course we want to figure out x next, the how far Otis lands from the base of the table. And so for part B, we can use our horizontal equation, which is Vx times time I am using the calculator's answer for time, so not this one so much, but the 0.52915, and we get a distance of 1.59 meters. For this type of problem, where an object is moving horizontally over a cliff and then kind of falling, yeah, many people will forget this. This is the one thing that people forget the most, is that when things are dropping, this vertical velocity, the vertical velocity at time zero, which is when the cat is just off the table, is zero. Cool. Let's continue. Imagine we have a soccer ball and we are kicking it up and to the right with a initial velocity of 11 meters per second at an angle of 23 degrees above the ground. The ball will make a trajectory, looks something like that. This will be its path through the air. And okay, I didn't draw that trajectory perfectly, that's fine. We want to know how long is the soccer ball in the air and how far horizontally does it go. So this is x naught, what is x over here? And we want to know how much time does it take to land over here. Cool, so let's put 0 for x naught. And let's just talk about the heights real quick. So the initial height is the ground, which is 0. The final height of the soccer ball is the ground, which is 0. Now let's talk about the velocity. Oh, and we can put a as negative 10. Okay, so the velocity, where does this, think about, where does this 11 meters per second go? Is it a horizontal velocity? Is it the initial vertical velocity? Is it the vertical velocity somewhere later in time? And of course, the answer is none of these. We have a vector, a velocity vector at an angle. And so what we want to do is break this up into components. We have component Vx, and we have a component Vy naught. And let me go back here. This is not just a velocity, this is the initial velocity of the soccer ball. So this is the initial velocity. This would give us the initial vertical velocity, the component Vy naught. And yeah, part of me wants to say, the initial horizontal velocity, but since it's constant, it's not only the initial velocity horizontally, it's the horizontal velocity throughout the whole trajectory here. So we're just going to write Vx. And so we're going to do these real quick. Vx equals V naught cosine theta, and Vy naught, well, let's do this on the side here. Vy naught is V naught sine theta. So V naught is 11 cosine of 23. Type that in. And I get 10.13 meters per second. And for Vy naught, 11 sine 23, which is 4.3 meters per second. Cool. And these numbers go straight into our lists. So Vx is 10.13 meters per second and 4.3 meters per second. Cool. And it's similar to our last problem where we have the same values, not the same values, but we have the same variables known. And so we're going to find the time and then we're going to find x. So for part A, we'll use the same trick. Y equals y naught plus v y naught t plus 1/2 at squared. 0 equals 0. This one's 0. Vy naught is 4.3 times the time unknown plus 1/2 negative 10 t squared. This is 4.3t minus 5t squared, which will add 5t squared to both sides. We get this. Now, if you know your algebra, there's two solutions for t that we're going to get here. One of them is 0. One of them is 0, which is not the one we want. So clearly, we don't want the time that's 0 because this is going to take some time that's not 0 to get over here. So wouldn't do this in math class, but we're going to divide both sides by a t, which gets rid of one of those exponents there. We get 5t equals 4.3. This is the solution for t that we want. So it's just 4.3 divided by 5. T is 0.86 seconds. We'll bring it over here. 0.86 seconds. And now we'll do part B. And we're trying to solve for x. Vx is 10.13 times 0.86. Something like 8.7 meters, 8.71 meters. Cool. So in a way, these problems, like the soccer ball problem, they take a little bit longer having to figure out components, but you get these numbers right out of the equations, Vx and Vy naught. And so this one, you have to remember when an object's moving horizontally off like a cliff or something, we get Vx, but Vy naught, remember it's dropping, so it's 0. Okay, so one thing I would just point out before we end this video, I'll just draw it again. Going back to this motion, where we have the ground, and we have some object that's launched at an angle, and it makes this trajectory through the air. So something to note here is that here's the initial velocity, and it's got a horizontal component to its velocity, and it has a vertical component. I think I changed the colors. Let's do purple. So this is Vx, and this is Vy naught. Now, for some other location in its trajectory, maybe I'll use black for this other locations. Maybe here, maybe here. Let's go here. So these are just points where the object will be in its trajectory. Let's note one thing here. So Vx never changes, so the length of this component always stays the same. I tried my best to do that. These are all Vx, unchanging. But Vy changes. Vertically, it will be losing speed, so maybe let's say it'll be about here. Here there is zero vertical velocity. Vy is zero. And then down here, oops, let's make that straight. And then down here, something like this. Okay, so these are all Vy. Okay, this is Vy, but there's zero magnitude for it. This is Vy, and this is Vy, which is not the velocity of the object. The velocity of the object would be a vector about right here. This would be V. This would be V naught. V would be essentially what Vx is, because Vy is 0. And then here, this would be V. And then something like this. This would be V. So, a couple of things to note. The vertical velocity is 0 at the highest point in the trajectory, the maximum height. And so the velocity vector is equal to Vx in that case, but otherwise it's different in at these other locations. There's a bit of symmetry to this. If we're using our numbers from the last problem, 11 meters per second at 23 degrees, let's say this is 11 meters per second at 23 degrees. When it lands, the same height over here, this will also be 11 meters per second, and this angle would be negative 23 degrees, okay, over here. So that might help you with your homework, and that's all we have for this video.